I'm your host, Vince Gucic, and you can find past shows on YouTube. Look on the channel Vince5305. That's VINCE 5305. Today, I want to go into sort of a long discussion of what makes a planet habitable, whether it's one that we find with telescopes like the Kepler telescope, the exoplanets outside our solar system, or our Earth, or even Mars if you consider a colony like Elon Musk is, along with some other people. So, start off. I've got a picture. John, can you get a picture of this? John Nelson's in the studio helping me. It's a picture of the frequency of colliding body impacts with the Earth, asteroids, comets, you name it. And it's according to size. Okay, 1 micron diameter particles, you don't even see them, every 30 microseconds. A millimeter diameter, a tiny, tiny fragment of a meteorite every 30 seconds. A meter in diameter every year. I wasn't aware of that. 100 meter diameter, which is pretty damaging, that's every 10,000 years. And there's about 3 near that category. Okay, one of them was Tunguska, a meteor that hit in Siberia in 1908, and it flattened 2,000 square kilometers of forest. People thought it was so powerful. Was it antimatter? No, just a big piece of rock. Another one was Taupo, and I believe that was about 1,500 years ago in New Zealand. Left a beautiful lake, but must have obliterated most of what used to be New Zealand wildlife. And finally, there's Toba, 70,000 years ago, and that was in Indonesia, and it possibly killed off so many humans that we went through a small population size, therefore a genetic bottleneck. One of the pieces of evidence is that we have pretty low genetic variability for a population our size. And of course there's Chicxulub, the one that either did or helped extinguish the dinosaurs 65 million years ago. So part of habitability is not being hit, at least not while you're a species. So another example here, other than saying pick the right planet, is stay away with places that start with T, Tunguska, Taupo, Toba, or C, Chicxulub. Well, you know, there's lots of other things that have happened. So one of the reasons that our planet is habitable, not having too frequent collisions with massive bodies, is Jupiter exists and it clears out most of the nasties in our orbit. But there's lots more, and let's get into that. All right, so we know our planet is habitable. Some people believe that other planets, even potentially accessible remotely or by travel, do have life. Now, the closest Earth-like planet, about the right size and possibly the right temperature and so on, is 1,400 light years away. So if we wanted to have a conversation with those life forms, it's 2,800 years each way, not very practical. Now, there is another planet around Proxima Centauri b, our nearest neighbor star other than the Sun. That's 4.2 light years away. And even though Proxima Centauri b is pretty small and cool as a star, the planet around it that it was found is pretty close to it. So it could have about the right temperature. Well, anyway, people have been searching for habitable planets a number of different ways. There's the SETI program, which looks for communication from intelligent life forms, and we can go into that. They haven't heard anything yet, and they've been active, I think, 53 years. Another way is to use telescopes that detect planets a number of different ways. One of them is by partially blocking a little bit of the light from the star as the planet passes in our line of view between us and the star. Okay, that's one. Another way is to find a wobble in a star because the planet is going around it. Well, this helps if it's going side to side, so the orbit is face on to us rather than edge on. And that way you can see the star being pulled one way or another. These are really, really sensitive measurements. It's amazing that people do it. So I put together my own set of considerations about what makes a planet habitable. There are a number of other people who've done this. One of the books, John, can you grab a picture of that? Oh, I don't know. I'll walk over to you. Pardon me a second. Okay, is that on? It's out of focus. Oh, get it with your phone then. Actually, get a picture of that with your phone. That'd be easy. Okay, we're experimenting a bit with taking videos of the show to put into YouTube with some, I'd say, better action that demonstrates things. So anyway, the book that I asked John to take a picture of is Earth's Biosphere, and it's by this great geographer, Václav Smil. He's at the University of Manitoba. He's written a whole series of books. That book, Earth's Biosphere, goes into habitability of a planet. I've pulled together some aspects that are similar to what he does and some others that are more novel. Well, not necessarily novel with me, but I think I've got a good synthesis of all this. Okay, you obviously have to have the right temperature, meaning a bright enough star at the right distance and one that doesn't flare up and so on. And you need the radiation that it gives for photosynthesis because that's going to be the way that life on other planets sustains itself as it does on the Earth. Everything we eat and a lot of stuff that we wear and build with, wood and so on, depends on photosynthesis. Now, I focused on radiation, electromagnetic radiation, for a number of reasons. One of them is that the ultimate balance of energy at the surface of a planet, other than some that has a huge internal energy source, is radiation from the nearby star, like our sun. And that's the only way we get any significant energy from the sun. Well, there's some particle emissions, but they're tiny compared to the radiant energy that we think of as sunlight, but it also extends into things we can't see, the ultraviolet, the infrared, all of which are important. And the only way that that energy leaves the Earth rather than accumulating is by radiating out to space as thermal infrared at longer wavelengths, but with many, many more particles of energy, the photons. Now, another thing that you need on a planet to be habitable is the right set of chemical elements. And for the Earth, that's sort of a happenstance of being in a solar nebula at the start that had been enriched with lots of other chemical elements over and above hydrogen and helium from the Big Bang, because either a supernova or a neutron-star merger created a massive outburst of element formation, nucleosynthesis, creating everything heavier than helium. Well, there was a little lithium too. And then those elements have to be kept available constantly for life. We'll go into what chemical elements we need. There's maybe 20 or so for us alone. And that is thanks to this R process. It goes certainly up to iodine. Okay, that's element number 54. That's even beyond the most stable element, iron. Okay, and then of course we're going to need water and carbon, and I'll argue why water and carbon are it. Forget about silicon, forget about ammonia as a medium for life, and there's very good chemical and physical reasons for that. And then of course you're going to need an atmosphere on the planet. You might have a small planet near us, well, think of the moon even, and that wouldn't retain its atmosphere because the molecules that are moving around at the right temperature for life also can escape to space in small quantities, but in the end, all of them. So then you've got something like the moon. The moon isn't terribly small compared to some of the planets and dwarf planets, but it did lose everything. So anyway, backtracking a bit, Frank Drake in 1961 posited an equation for how many planets in our galaxy harbor intelligent life. And he just multiplied probabilities. The average rate of star formation in our galaxy multiplied by the fraction of stars that have planets, multiplied by the average number of planets per star that can support life, and then multiplied by several more factors. Okay, why star formation? Well, because stars don't last forever. So we have to have a fresh star to give us a run at evolving life. And the fraction of stars having planets, yeah, that's pretty high. I think the average that's been found now, by careful looking, is about a half. And then the average number of planets per star that can support life, that's a tricky part. Now, all of these things might not be independent probabilities, but in any case, there's the argument that there's habitable planets with intelligent life somewhere in the galaxy, and I don't remember how many he estimated would be possible. Okay, let's start now with some other details, like getting the temperature right. Okay, what is the right temperature for life? We know what we're comfortable with. We know what kinds of physiological and cultural acclimations we have to give us a range of temperatures that we can exist in. So there are people who live in Siberia that goes down to minus 60 Celsius, and there's people who live in the Danakil Desert that goes up to plus 50 Celsius, and a lot of that is cultural adaptation. You better have clothes, right? Well, I suppose intelligent life is likely to have clothes anywhere. And then you can look at some other forms of life, like the organisms that live in the hot springs in Yellowstone National Park, which is an interesting story, too, because that's where this tool for this DNA polymerase that can withstand high temperatures was found, and it ultimately gave us the basis for the polymerase chain reaction for lots of DNA studies. But that's a side story. You can even say that there are some even hotter places deep in the ocean at the geothermal vents, the black smokers. But everything like the proteins that needs to stay working is stabilized there by the high pressures. So we're not going to count on life being in these very high pressures. Okay, so what's next? Well, I'll get into some of the energy balance stuff in a little bit, but first let's say, what if you've got a planet that's near the right star and at the right distance, and on the average it has about the right temperature, but then the average is the tricky part. That's not a good measure.